Welcome to springlib.
Hello everyone, today we're doing chapter 18, problem 44, and this problem asks us for A and B, given that these designs with these reagents, why won't the product A and B be formed? Give a reason why, and then design a synthesis for A and B from benzene, A from benzene and B from phenol to obtain the products here. So let's look at A. So A, we're starting with an electron withdrawing group. So we know that electron withdrawing groups direct meta. And then we're doing Friedel-Crafts acylation with halogenation afterwards. But here's the thing. Step one is Friedel-Crafts acylation. And what we learned in the textbook is that Friedel-Crafts reactions, whether it's acylation or alkylations, cannot occur on deactivated benzene rings. This SO3H group is taking away electron density out of the benzene ring and onto itself. So this is actually making the benzene ring more electron poor because it's an electron withdrawing group. So in this reaction is a type of electrophilic aromatic substitution. So for this reaction, your benzene ring must act as your nucleophile. But in order for your benzene ring to act as a nucleophile, it must be electron rich. So you need electron donating groups to allow nucleophilic attack from your benzene to your electrophilic carbonyl group here. However, because it's actually electron withdrawing, your benzene is going to be electron poor, so it cannot actually act as a nucleophile in this reaction. So step one will not go. And even if step one did go, even if we did get meta-directing addition of your group here, step two wouldn't occur because you would get step two having a meta directed, like in this position, not paired to the sulfonyl group here. And that's because your ester is a stronger meta director than the sulfonyl group here. So you would get addition of rechlorine at this carbon and not this one. So an alternative from starting from benzene to form product A So we start from benzene. An alternative is, well, let's first add our chlorine group. So we'll add diatomic chlorine and our catalyst to add a chlorine group here. And what we know about chlorine and halides is that they are ortho and para-directing. So what we can do then is that we know that we need this group here that is going to be ortho to the chlorine. So we can just say that we're going to add the reagents of step one. Well, it's just 2 carbons. And we will get both the ortho and the para substituted product, but we're only interested in the ortho product. But we will isolate this ortho product and move forward. And then we can add this SO3H. Why? Well, because we know that this carbonyl group is meta-directing. And we know that this chlorine group would be ortho and meta and para-directing as well. So we get double substituted products here, double direction on these 2 carbons here. So we would obtain with one of the isomers being our desired product, chlorine with the ketone, and then our desired product would be the one in which the SO3H is opposite to the chlorine, and that would be this carbon here. And then obviously we would form the isomer with the SO3H adjacent to the chlorine as well. Oh. But this is our product of interest. So now in B, let's see why B doesn't work as is shown here. So we have a methoxy group, and we know methoxy groups are electron donating because oxygen can donate through resonance a carbanion into the benzene ring, making it highly electron rich. So we know the electron donating groups are ortho-para-directing. And then we have Friedel-Crafts alkylation. But now the issue is with this Friedel-Crafts alkylation is that this alkyl group is on a primary alkyl halide group here. So we would essentially form a primary carbocation, but what we know from past chapters is that primary carbocations are highly unstable. So what's going to happen is there's going to be a 1,2 hydride shift to form a secondary carbocation, and then you would get some sort of butyl group that would be introduced as a side chain. So you won't get the straight chain beautiful alkane. You would get something that looks like this attached on it. You wouldn't get your straight chain. So because of that rearrangement, we need this proposed synthesis would not occur as shown here. So the question is saying that let's start with a phenyl group and try to synthesize B. So first things first, we know that we want a methoxy from this alcohol. So let's get the methoxy. So we'll add our alkyl halide with sodium hydride. Sodium hydride will deprotonate your alcohol to make it a very strong nucleophile, which would go through SN2 backside nucleophilic attack to gain 1 carbon. And step 1, step 2. And now we gained our methoxy group. And now with this methoxy group, what we can do now is we know that we wanted the para-substituted addition of these carbons. So we won't do Friedel-Crafts alkylation, we'll do Friedel-Crafts acylation. So we'll add the acyl group with the appropriate number of carbons. So we want 1, 2, 3, 4 carbons. We have 1, 2, 3, 4 carbons with our Lewis acid. And we will get 2 isomers, one being the ortho, one being the para of interest. So we get the ortho, 1, 2, 3, 4, and then the para that we're actually interested in. One, 2, 3, 4, and we'll take this para, and now we want to just reduce it such that this carbonyl group will be reduced to a CH2, and to give the straight chain alkane that we have in our product. So we'll use zinc, mercury, in a strong acid. And this is a reducing agent that has been used in the textbook and past problems. So 1, 2, 3, 4. And now what we have is 2 directing groups. We have ortho pair directing from this methoxy, and we have ortho pair directing from the alkane bond here. But in terms of the strength, the methoxy is a lot stronger directing group than this alkyl group here because of the fact that the methoxy is actually donating electron density through resonance, while this alkyl group is donating, the straight chain carbon group is donating through inductive donation of its electron density. So because this oxygen atom has lone pair electrons and actually donating through resonance, this is a stronger directing group. So we know that our addition product is going to occur on one of these 2 carbons, which is actually what we want. We want this nitro group to be adjacent to or ortho to this methoxy group that we have here. So we'll add that nitro group with nitric acid. and sulfuric acid. And we will get product B, an exclusive product. Doesn't matter which ortho position you choose because they're both identical because of the internal plane of symmetry. 1, 2, 3, 4. And then we'll add our nitro group here to obtain B.